So today we're going to be learning about surface integrals. It's lesson 17.7 in our Calc 3 textbook. And surface integrals, they tell us basically the surface area of different objects and different vector equations that we get that create 3D shapes. And they can also tell us flow, flux. So it's applicable to a lot of physics-y stuff. So for warm-up, we're going to be going over a line integral. We're going to evaluate the line integral z dx plus x dy plus y dz. And we are given that c is x equals t squared, y equals t cubed, and z equals t squared. So first thing that we're going to want to do is obviously convert all these dx's and these dy's and dz's into dt's. And in order to do that, we have to find dx over dt, dy over dt, and dz over dt. So let's... And so those equal 2t, 3t squared, and 2t as well. So then dx equals 2t dt. Dy equals 3t squared dt, and dz equals 2t dt as well. And so from that, we can just substitute all the x, y's, and z's for t's. And that'll give us t squared 2t dt plus t squared 3t squared dt plus t cubed 2t dt. And then we can we can add up our like terms, or rather combine our like terms. So we get that, and then we can just integrate all those, and we are left plus 3/4 t to the fourth plus 2/5. I'm sorry, that should be 5, and that should also be 5. It's 3/5 t to the fifth plus 2/5 t to the fifth. And then this just equals 3 over 2. So with surface integrals, say we have a vector equation given below, right here. R of u comma v equals x of u comma vi plus y equals y of u comma vj plus z of u comma vk. U and v will create some sort of domain, and its dimensions will probably make a rectangle of sorts, and that domain will be called D, as shown in the example to the right. And so that domain of D will allow us to find the area of the surface of the vector equation. And the way we do that is by dividing the domain D into very small rectangles, the size of change in U and change in V. Those would be the dimensions of the rectangles. And then from there, we would evaluate using this vector function right here. And then once we find that, we would assign the area, the one rectangle area, to that value, and then we do the same for all the rectangles within the domain, and then we sum them all up to find the total surface area. And that's what is being expressed here in this definition of the surface integral, and it looks very similar to many other surface integrals because it's mostly the same. Obviously, we're doing a little different. Surface integrals, they tend to mimic double integrals with the way that they're set up, but what we're trying to find is not necessarily the volume necessarily. We're trying to find, obviously, the surface area. And so we do that by finding a rectangle that lays on a surface of the vector equation, and we make that rectangle small enough where, say, we have a surface here, we make a rectangle small enough that it lays on this surface, and it basically you can ignore the curvature of that surface. The rectangle is just that small. And how we find this rectangle, we find r of u. These are the vectors r of u and r of v, and we take the cross product of the two, and then once again we assign an area, change in v times change in u, so that rectangle right here, and r of u is equal to dx over du times I plus dy over duj plus dz over duk, and the same thing goes for rv, except for instead of du you have dv. And so once you find the cross product and the magnitude, you can assign your area to that specific magnitude, and then you can integrate that sum, and you multiply obviously by this function f of r of u comma v, and you would integrate by dv and du. That's what dA is. dA is just basically you're summing together, or rather multiplying together dv and du. And so we initially had this function right here, f of x, y, and z. What we do is we convert that function into basically a function that can be expressed with two variables, whether that be phi and theta, or r and theta, or maybe z and theta. Basically any two variables that can express x, y, and z. And then by doing that and multiplying by the magnitude of the cross product, we can convert this into this new integral. And then from there we can find we can evaluate surface integrals. So example 1 has us finding, or rather evaluating, the surface integral x squared, where s is the unit sphere, x squared plus y squared plus z squared equals 1. So we're going to want to convert x squared plus y squared plus z squared equals 1 into some sort of equation that has two variables that can express it. And so since this right here is just the sphere of radius 1 centered at the origin, I think the best way to convert this would be to use angles phi and theta. So that's exactly what we're going to do. If you remember from polar coordinates in the three-dimensional, x equals sine phi cosine theta, y equals sine phi sine theta, and z equals cosine phi. And so with this information, you can now figure out what r phi is, which is equal to cosine theta cosine phi I plus sine theta cosine phi j minus sine phi k. And then r of theta is equal to negative sine phi sine theta I plus sine phi cosine theta j plus. So now that you got r theta and r phi, you take the cross product of the two, and then also take its magnitude. And I don't want to digress too much into the cross product calculations, but it basically equals out to sine theta you take the cross product, and then you square each value, and then you get a whole lot of sine squared fees and cosine squared fees, and then you can combine them using Pythagorean law. And so once you've gotten r phi and r theta, you take the cross product of the two, and then you take the magnitude of them. And I don't want to get too deep into the cross product calculations, but it eventually just equals sine phi. So you find the cross product, you square all the values in the cross product, and then square root it to find the magnitude, and you're left with a lot of sine squared thetas and phis, along with some cosine squared thetas and phis. They can be added together and combined to equal 1, and then you're just left with sine phi. And so once you get that, you can plug that into this equation up here. So you have x squared, which you should express as using your two variables, your phis and thetas. And so you're going to express it as sine phi cosine theta squared, and then multiplied by sine phi, and then d phi d theta. So once you got this, you can now separate the phis and thetas into their own integrals and multiply them together. And so phi and theta, since we're talking about the sphere centered at 0, 0, 0, and with a radius of 1, phi is going to be between 0 and pi, and theta is going to be in between 0 and 2 pi. So those are going to be your upper and lower bounds. So we'll start with theta first, and we have cosine squared theta d theta, as well as sine cubed phi d phi. And then we can go ahead and integrate that, and using the half angle formula, or sorry, the double angle formula rather, we turn cosine squared theta into 0 plus half sine 2 theta. And then we multiply that by negative cosine phi plus 1/3 cosine cubed phi. And then you multiply that out to get 4 pi over 3. So in the last example, we showed how we can use angles phi and theta as our two u and v variables to express vector equations and thus find surface integrals. But we can also use the variables given to us, like x and y, to express those same vector equations. So what we would do is we would set x equal to x, y equal to y, and z equal to some function of x and y. So by doing this, it makes things a lot simpler for us in terms of finding Rx, or rather Ru and the cross product with Rv, and as well as the magnitude, because Ru is now just Rx and Rv is Ry. And so assuming that we use this setup, R of x is always going to equal I plus dg over dx, and g being the function of x and y, which z is equal to, times k. And R of y is always going to equal j plus dg over dy times k. And then the cross product of that is always going to be negative dg dxi minus dg dy j plus k, and the magnitude of that would be all these squared and then taking the square root of. So you have dz over dx squared plus dg over dy squared plus 1, all square rooted. And then that is now your formula that you can use whenever you use the function f of x comma y comma g of x comma y to represent f of x, y, and z. And so in this next problem, we're going to do just that. We have an equation z, or a function of z of x and y, and we are trying to integrate y. And so we can first go ahead and take the integral, or not the integral, rather, the derivative, dz of dx, which is 2, as well as derivative dz dy, which is also 2. And then with that, we can go ahead and, so since y is just equal to y, it can be expressed as such. So we can just say y as our function right here, square root dz dx squared, so that's 4, plus dz dy, which is also 4, plus 1, dA, which we can break that down to dx and dy. And our bounds are 0, 1, 0 to 1, and then 0 to 2. So we can go ahead and throw those in as well. 4 plus 4 plus 1 is 9. You take the square root of that, it's 3, so we can pull out the 3. And then we are left with dx and dy. So we can go ahead and evaluate our integral. That's supposed to be a 1, this is supposed to be a 2, and then we multiply that by 3. So we're left with 3, y squared times 2 is 4, divided by 2 is 2, and then that minus 0. So we're left with 6 as our answer. So one useful thing that we can use surface integrals for is finding the surface integral of a non-continuous object or shape. So one that has maybe a boundary, an edge, or a sharp curve that can't be that can't have. So when we're dealing with objects that have non-continuous surfaces, like any shapes that have hard edges or anything like that, what we can do is we can take multiple surface integrals and add them up together in order to get a total surface area. And so, for example, in this next example here, we have basically a laterally cut cylinder. So if you can see in the drawing, it has a base of x squared plus y squared, which is less than or equal to 1, so basically just a radius of 1 at the bottom. It's a cylinder, x squared plus y squared equals 1, and it is cut by the plane z equals 1 plus x. And so we have 3 different surfaces here, S1, which is basically the lateral face of the cylinder, S2, which is the bottom face of the cylinder, and then S3, which is the diagonally cut side of the cylinder. And so what we can do with that is essentially we can just take the different surfaces apart and integrate them and then add them together at the very end. So we have for surface 1, we probably want to use, since we're looking at cylindrical coordinates, we probably want to use some sort of height and and an angle. So theta and z will be the two variables that we use here. And so x would equal cosine theta, y would equal sine theta, and z would just equal z. And r theta times, or rather the cross product of r theta and rz would equal negative sine theta cosine theta 0, 0, 0, 1 at the bottom, and that would equal out to cosine theta I plus sine theta j. And then if we were to take the magnitude of that, we get cosine squared theta plus sine squared theta rather, and we would get 1. So that's the cross product magnitude of RZ. Let's write that. And then with that we can just plug in Z, since that's what we're evaluating. We're gonna plug in Z and multiply it by our cross product magnitude, which is just 1, and then it'll be in terms, or rather with respect to d theta and dz. And for our bounds, d theta obviously is 2 pi and 0, and then for dz, we're given that z is equal to 1 plus x and z is equal to 0, and those are our two bounds for side 1. So we're going to express 1 plus x in terms of theta, so that'll be 1 plus cosine theta, and then we can just write 0 at the bottom. And then from here, we can just go ahead and integrate, so we just have 0 and then dz is all that's left, and then we get 2 pi and dz. And then for our bounds, we have d theta, which will be 2 pi and 0, and then z, we have z equals 0 and 1 plus x, and we'll express 1 plus x in terms of theta, so that'll be 1 plus cosine theta and 0. And then we're actually going to switch d theta and dz, so instead it will be 1 plus cosine theta, and then 2 pi over 0, z times 1, and then dz, and then d theta. From there we can expand 1 plus cosine theta squared, and that equals 1 plus 2 cosine theta plus half 1 plus cosine 2 theta. We can just apply the double angle formula right now. D theta 2 pi, that should be 1/2 to 0. And then we can integrate that into 3/2 theta plus 2 sine theta plus 1/4 sine 2 theta at half. We combine this term with this term, half plus 1, you get 3/2 theta plus 2 sine theta, and then you have 2 pi. And then after that, we can solve and get 3 pi over 2. So both of these sine values, since it's by 2 pi and 0, they'll both be 0. So all we're left with is 3/2 theta. We plug in 2 pi for that, and then divide by 2, and we're left with 3 pi over 2. And then, so that's for side 1, but for side 2, side 2 is just x squared plus y squared is less than or equal to 1. But since side 2 is located entirely in z equals 0, so the xy plane, when we integrate that, since we're integrating z of ds, we're really just integrating 0, and that will also just be 0. Now for side 3, we're going to be using the equation z equals 1 plus x, and we're going to be using that as, well, so that's going to be equal to z, and then x is going to be equal to x, y is going to be equal to y. And so what we do with that now is we take the derivative, so dz dx, as well as the derivative for dz dy, and we are left with 1, and dz over dy is equal to 0. And so we can now plug that into our older equation to find r of x with the cross product of r of y, and we add that to 1 to find our magnitude, and then we will get 1 plus 0 plus 1, which equals root 2. And then so we have what we're integrating, z, which will be expressed as 1 plus x actually, times root 2, so we can pull that out to the side with respect to dx and dy. So since we're dealing with basically a circle as our third surface, the best thing that we can do is convert dx dy into polar coordinates for dr d theta. So that's what we'll do. Go root 2, and then our bounds are going to be 2 pi, 0, and 1, 0, and then we're going to make this 1 plus cosine theta dr d theta. And then we gotta multiply by r because we're converting to polar coordinates, and then we can multiply that out to get r plus r cosine theta dr d theta times root 2, and then we can go ahead and integrate, and then oops, there's also supposed to be an r there, so that's an r squared, and then this equals root 2 times 2 pi 1/2 plus cosine theta over 3 d theta. And then we can integrate this one more time, and we get theta over 2 plus sine theta over 3, all multiplied by root 2, from 0 to 2 pi, and then that equals root 2 pi. And then so that is our side 3, and so side 2 is 0, and then side 1 is 3 pi over 2, so we add these two sides together to get the total surface area. So the last concept that we're going to be talking about are oriented surfaces, and these are surfaces that have two sides and have basically tangent planes that are able to exist on each and every point of the surface integral, and thus having a unit vector going outward from those tangent planes and inward, perpendicular obviously. And so those two orientations, the positive and negative, are associated with outward and inward respectively. And an example of a non-oriented surface would be the Mobius strip, for example. Because it is actually one-sided, it's obviously it has a unit width, and then the it's only one-sided because right here there's a twist in the strip, and as a result, the back side, I guess what you can call it, connects to the front side. And so with this information, we can identify flow, flux, oriented surfaces. Another word for them, or what they're usually attributed to, are Gaussian surfaces, and that is usually discussed in Physics C regarding electric field. And it can also be used to measure the flow of fluid through something like, say, a fishing net, where the object isn't impeding the flow of whatever fluid or electric field is passing through it. And so we have all these vectors, n, these unit vectors, and in order to find the value of the unit vectors, assuming that we have a surface z equals g of x comma y, we're going to be using x and y as our UV variables, and then from that we can use the equation, the x and y equations for the cross product and cross product magnitude. And with any unit vector, obviously you have the cross product, and then below that you divide by the magnitude, and that gets you your unit vector. So that's what n equals. And so if we were to have a fluid, electric field, or even heat flowing through our oriented surface, and that fluid, electric field, or heat has some sort of density, whether it be just a certain amount of it in a single unit area, as well as a velocity, however fast it travels through time, we can multiply those two together, and we can get a single function, or a single vector field rather, of mass per unit time per unit area. And then with that, we can take that vector field f and take the dot product of that and n for all areas Sij. So basically all these little patches on the oriented surface, we're taking essentially every single directional vector and assigning it to a vector field f, and then we are integrating it. And by doing so, we then find the total flux of f over s. And this is just the surface integral of f over s. And so we can use this to find all sorts of things, and in Physics C, it's very much relevant with electric field when we're talking about Gaussian surfaces. And so we have this equation, or rather this integral right here, the dot product of f and n ds integrated. And so since we're going to want to convert f into a function of r u comma v, we do that by obviously changing ds to dA and multiplying by multiplying by ru rv, the cross product. And since it's we're also multiplying by the magnitude, this cross product magnitude, the fraction value at the bottom of n, which we have changed to, cancels out, and we're just left with the cross product ru cross rv. And so the remaining integral is simply f times the cross product of ru and rv dA. So for number 4, we're asked to find the flux of the vector field f of xyz equals zi plus yj plus xk across the unit sphere x squared plus y squared plus z squared. And so the first thing that we're going to do is we're going to convert f of x of yz into variables f of r, phi, and theta. And so this is cosine phi I plus sine phi sine theta j plus sine phi cosine theta k. And so now we can find r phi and r theta respectively, we can find r phi to be negative sine phi I plus cosine phi sine theta j plus cosine phi cosine theta k. And then r theta would be 0I plus sine phi cosine theta j minus sine phi sine theta k. And then when we take the cross product of the two, I'm going to skip the whole matrix. You can pause the video and figure it out for yourself. But the answer would be sine squared phi cosine theta I plus sine squared phi sine theta plus sine phi cosine phi k. And so we found that we know what f of r phi theta is, and we know what the cross product of r phi and r theta is. And so in our original equation, we have f, the dot product of f, and the cross product of r phi and r theta in our final integral. And phi is obviously between 0 and pi. And theta is between 0 and 2 pi. So we can add that into our integrators. And then we can multiply, or rather find the dot product of f and the cross product of r phi and r theta. And we're going to skip the calculations on that one as well. And we get 2 cosine theta sine squared phi cosine phi plus sine cubed phi sine squared theta d phi d theta. And so we can now separate each of these quantities into two parts from phi and from theta. And so that leaves us with 2 sine squared phi cosine phi d phi times 2 pi to 0 for 2 cosine theta. And as you can see, you're breaking up the thetas and the phis, and then you do the exact same with this other quantity here, sine cubed phi, and then 2 pi for sine squared d theta. And so you can simplify this down. So 2 cosine theta d theta from 2 pi to 0, this actually right here, this is actually equal to 0. So this entire quantity right here can basically be crossed out since you're multiplying by 0 here, and then you're left with pi to 0 for sine cubed phi 2 pi sine squared theta d theta. And then this is almost the exact same problem that we were left with back in number 2. And so we can go ahead and integrate this, and sine cubed phi is equal to sine phi minus sine phi cosine squared phi d phi. And then we can use the double angle formula for sine squared. And we would get 1/2 times the integral of 1 plus cosine 2 theta d theta. And then we can finish off our integral here. Cosine phi plus 1/3 cosine cubed phi pi 0, and then times theta plus 1/2 sine 2 theta 2 pi 0. And so this eventually multiplies out, since this is the exact same quantity that we were left with in number 2. This also ends up equaling 4 pi over 3.